Welcome to this explainer. Have you ever looked at a screen just completely full of computer code and thought, wow, that looks like an alien language? Well, you're definitely not alone. It looks exactly like that to almost everyone at first. But today, we're going to translate all that abstract code into intuitive, visual analogies. We're essentially breaking down how computers actually think. So get comfortable, because we're going to completely demystify the blueprint of logic itself.
Okay, let's dive into this. Here's our structured roadmap for the explainer. We're starting with decoding programming versus coding. Then we'll hit the building blocks of logic. Third is algorithms and the phone book method. Fourth, architecting software using OOP and MVC. And finally, mastering the coding mindset. All right, let's get into it.
Section 1, Decoding Programming versus Coding. Let's tackle our first major hurdle and clear up a massive misconception right out of the gate. People use these two terms interchangeably all the time, right? But they actually represent entirely different scopes of work. Think of it like a kitchen. Coding, that's the act of writing out the specific instructions. It's literally translating your ideas into a specific language, like Python or JavaScript. Basically, you're just writing the recipe. Programming, on the other hand, is designing the entire meal. It includes coding, sure, but it's so much bigger than that. It's the planning, the problem-solving, testing, and improving the systems. You're choosing the ingredients and ensuring everything works perfectly together long before you even type a single line of code.
Moving right along to Section 2, the building blocks of logic. We're transitioning from that high-level concept down into the microscopic rules that actually make a computer think.
So every single piece of software in the world relies on this triad of foundational logic. First, you have sequence, which is just arranging and executing commands in a specific sequential order. Simple enough. But things get really interesting with selection. Think of these as decision forks in the road. You know, your classic if-else statements, where the program has to make a choice based on a specific condition. And finally, to avoid doing the exact same work twice, we use iteration, or loops. This is how a computer instantly handles repeatable tasks over and over until a condition is met, saving you from writing the exact same code a million times.
Now, to actually make those logic blocks work, we absolutely need variables. I want you to visualize a variable as a physical box sitting on a shelf holding specific ingredients for our recipe. Say, a box labeled name that holds the word Alice. It's just a container, but it gives the computer a reliable way to understand, store, and manipulate the data we're feeding it.
And this brilliantly illustrates what happens at the absolute lowest level of the machine. Everything, and I mean everything, boils down to Boolean logic, ones and zeros, true or false. It's exactly like a physical transistor on a motherboard, either allowing electricity to flow or stopping it dead. A 1 is true, a 0 is false. By stringing together billions of these tiny true and false decisions every single second, we can build those incredibly complex and powerful systems we use every day. All right, Section 3, Algorithms in the phone book method. Let's shift our focus to how we use those building blocks to write algorithms, which are really just formalized ways of giving instructions. Imagine you need to find the name Mike Smith in a giant physical phone book. The slow way to do this, opening to the very first page, checking for Mike, and if he isn't there, flipping to the next page and doing it all over again. You've got a sequence, a condition, and a loop all in action here. It absolutely works, but imagine doing that for 10,000 pages. It's wildly inefficient, right?
Let's contrast that with a much smarter algorithm. You open to the exact middle of the book. If the name Mike Smith comes earlier in the alphabet, you literally tear the book in half and throw away the entire right side. If it's later, you discard the left side. Then you repeat the process. This is the magic of computational complexity.
Think about it. If our phone book doubled in size next year, our first, slow algorithm would take thousands of extra steps. But this smarter method, it only takes exactly one extra step to cut the entire problem in half again.
Let's move to and see how this builds visually. To make those lightning-fast searches possible, computers organize data into specialized structures, like what we call a trie. Notice how words like tree, trie, algo, and string don't just sit in a massive flat list. Instead, they structurally branch out, letter by letter, starting from a single root node at the top. It's like a giant puzzle. Now look at the paths branching out here. On the left side, if the computer searches for the prefix str, it successfully follows the node straight down to find a match. Awesome. But on the right, searching for the word true navigates down to T, then to R, but hits a dead end instantly because the U node is missing. It fails immediately rather than scanning a massive database line by line. That right there is exactly how computers organize data to make those searches lightning fast. Moving to Section 4, Architecting Software with OOP and MVC. Let's zoom out from those microscopic algorithms and look at the macroscopic structures that hold massive web apps together. When you're building really large-scale software, Object-Oriented Programming, or OOP, gives you structural integrity through four main pillars. First, encapsulation, bundling data and methods into a single unit, kind of like a physical medicine capsule. Then, abstraction, which hides the complex details to show only relevant features. It's just like driving a car. You don't need to understand the combustion engine to turn the steering wheel. Then there's inheritance, allowing a child class to reuse properties from a parent, which saves tons of time. And finally, polymorphism, which lets objects dynamically adapt and take on varied forms to represent different behaviors.
Now, what's really interesting about this slide is how we apply these structural concepts to web apps using the MVC pattern, Model, View, Controller. Think of your favorite restaurant. The view, that's the waiter handing you the user-facing menu. The controller is the kitchen, receiving your order and executing the actual logic of cooking. And the model is the pantry, securely managing all the ingredients and data. Notice how the waiter never ever goes straight into the pantry to grab food. Everything is safely and beautifully coordinated through the kitchen. That's MVC in a nutshell.
And finally, Section 5, Mastering the Coding Mindset. Let's bring all these abstract concepts back down to reality and map out how you can start building your own programming brain. Look, you really don't need to lock yourself in a basement for hours to learn this stuff. Just 10 to 15 minutes a day can build incredible habits. Try solving just one small problem on a site like LeetCode. Go read other people's code on GitHub like you're reading a book, just to see how they approach things. Spend a few minutes reviewing and debugging your old code. Keep a quick coding journal to track your aha moments, or hey, simply learn one new command line shortcut a day. Daily consistency beats a marathon all-nighter screen session every single time.
So, the crucial point is this. You don't need marathon sessions to get better at coding. Consistency is key. A little bit every day builds lasting skill, and confidence when it counts. Small, consistent daily steps are literally the secret to internalizing this logic.
At the end of the day, it's all about taking that logical framework, sequence, selection, iteration, and applying it to the real world around you. So, I want to leave you with this provocative thought as we wrap up this explainer. What problem will you solve today? Start small, stay consistent, and just keep building that programming brain. Thanks so much for joining me, and I'll see you next time.